Welcome to the course on power quality. We were discussing last time also multipulse converter. Today of course, the outline with this we will talk about the classification of unconventional multipulse AC/DC converter. Unconventional multipulse converters we call it, which are not multiple of 3, because input supply is usually 3 phase. So, we have already discussed that usually the most of the converter are multiple of the 6, because single unit of the converter is with the 6 pulse, but these are the converter which are not multiple of the 6, that is we call it unconventional, the multipulse converter. And first we like to discuss 20 pulse and 40 pulse AC/DC converter with the design, simulated performance, comparative evaluation. Then we will go for 28 pulse and 56 pulse converters. Then of course, we will talk about design, simulation and comparative evaluation. Then we will go for 44 pulse and 88 pulse converters. Of course, going to be more than that, I think the TAD reduces drastically down. So, we do not go normally more than that. So, we will talk about again simulated performance, comparative performance also. So, coming to the classification, we of course can classify this unconventional multipulse converter into 2 categories. It can be non-isolated or it can be isolated converters, because if you, in some application you want isolation also, moreover you want to change the voltage level which are of the grid voltage to appropriate voltage which you want to apply for. And well, you have now here typically the further classification of your non-conventional as well as your non-isolated and isolated one, hybrid of phase staggering and multi-phase with the 20 pulse typically, 28 pulse and 44 pulse. And here also you have again for typically further, if you really have a ripple injection also to 40 pulse, 56 pulse and 88 pulse. Well, what we do in this case, we convert either with the auto connected. In non-isolated converters we use the you can call it like a typically auto connection or auto transformers, and to convert of course the 3 concept we will talk about, and another is isolated, we use the isolated transformer for that. And we have a concept virtually you can call it like even in even we can have a 10 pulse, then typically 14 pulse and 22 pulse. Originally with the you can call it, we convert 3 phase supply into 5 phase, which results the 10 pulse converter, and we have a typically phase staggering. So, we have 2 sets of 10 pulse converter which gave us 20 pulse converter. Similarly, we convert 7 phase into 3 phase supply into 7 phase, and from 7 phase we realize 14 pulse converter, and with the phase staggering we realize the 2 sets of 14 pulse. So, that give us 28 pulse, and similarly we convert 3 phase supply into the 11 phase supply, which give us after rectification by a converter of 22 pulse, and when we have a 2 sets of with the phase staggering we have a 44 pulse. Now, these converters further if we have a ripple injection, even in case of the uncontrolled like a diode rectifier with the pulse doubling. So, we can have this 20 pulse into 40 pulse, and like a 28 pulse goes to 56 and 44 goes to 88 pulse like. So, there are 3 concept in multipulse converter. The first is the number of the multi-phase concept, we are using multi-phase. Then second concept is the phase staggering, that also we are using in this case, and then we have a third concept like we call it ripple injection. So, all 3 concept in these 40 pulse, 56 pulse and 88 pulse converter, we are using all 3 concept like of typically of phase staggering, multi-phase and ripple injection. So, these are the 3 techniques which we use in multiple, and these are the interesting converter to increase the number of pulses and reduce the TAD of supply current, total harmonic distortion of supply current, and getting a good quality of output voltage with less ripple as well as the less ripple factor, we are able to go with these number of pulses like. So, coming to like first typically from 20 and 40 pulse converters, here you can just see clearly this even in case of non-isolated, first we are taking non-isolated. So, we are using, that is the reason we are taking auto transformer. So, 3 phase supply with the help of this Polygon auto transformer, we are converting this 3 phase supply into 2 5 phase supply. So, this is 5 phase, this is another 5 phase, 2 sets of 5 phase which are phase staggered from each other, and then you have a 10 pulse converter, another 10 pulse converter, and of course, we combine together because it is a auto connection. So, we can connect them in parallel, but we use the here certainly the interface transformer. So, that the current is equally divided into both, and that we are able to feed certainly for the load. Load may be like a simple, if we call it like a vector control induction motor drive or any other load for which you require input power quality improvement, like, but there may be another load also which require kind of DC voltage source with the unidirectional power flow. So, drive may be one of the area like So, now 5 phase is converted into 12 pulse, another 5 phase with the phase staggering. So, 3 phase converted to 5 phase of 2 sets, as we were considering in case of the 12 pulse converter, the 3 phase input supply we were converting to 2 sets of 3 phase with the phase staggering of 30 degree. Here we are converting 3 phase supply into 2 sets of 5 phase again with the phase staggering, and 5 phase means 360 by 5. So, they will have a typically 72 degree phase shift from one phase to the another, and that is the reason it is giving 5 phase, and this is another set of 5 phase, and this auto connected transformer is able to provide us this phase conversion from 3 phase to 2 5 phase supply like for this. And this is typically the how the transformer this transformer connection is there, that is the input voltage and these are the 2 sets of 3 phase, like this is one phase one set, and this is another set of typically for providing this auto connection of this. And well, so this now from this typically we can have of course another transformer connection also. This you can talk it typically maybe a T connection transformer, which here also we can have a 10 pulse, and then with this ZSBT 0 sequence blocking transformer we use it, so that you do not have a circulating current, and then we have a pulse ripple pulse doubling with the help of this interface transformer with the 2 diodes, and of course, this is the filter, inductor and capacitor. So, with this we are able to get 40 pulse. So, this 10 pulse 12 pulse give us a 20 pulse, and from 20 pulse doubling we do, you can call it like a 40 pulse. So, that is what we are getting 40 pulse converter. In this case you can typically get, we are using the multi-phase concept to convert 3 phase to 5 phase, 2 sets of 5 phase, then we are using phase staggering, so that we get the typically phase shift. So, here you can call it the pulse duration will be 360 by 40, and that is the same angle we do the phase typically kind of phase staggering, and then we have a ripple injection or pulse doubling here. In diode we can do pulse doubling, but of course, if it could have been a control converter with a thyristor, you could have increased the number of pulses, not only double, but 3 times 4 times, which we discussed in the last lecture like. And this is the typically the phasor diagram which we are mentioning it. Like you have a typically the phase staggering here. This comes the phase staggering, the concept of multi-phase, and then the phase staggering, the angle how you are getting that a one sets of the 5 phase, that you from this original voltage you are getting one set of 5 phase. Typically this is, you can call it 72 degree, 18 plus 54, that is virtually 72 degree, and you have another like a typically VC1, then VD1 and VE1. This is one set of 5 phase, this is second set of 5 phase which is of lagging from original supply by 9 degree, and that is typically you can call it like a VB2, VC2, VD2 and VE2. So, you get a 2 sets of 5 phase, and the phase staggering is between them is 18 degree. That is nothing but you can call it like a why it comes 18 degree, that is your 360 degree divided by 40 pulse. So, you will get typically here the 9 degree phase shift between the 2 plus minus 9 degree kind of phase shift like or so. So, that give you the typically the, you can call it the 40 pulses in the out, that give like a virtually your 20 pulses. This will be like a 20 pulses, but you have a again the phase typically pulse doubling, that give you like a 40 pulse here. So, that is the basic concept how we are getting, but you can understand the in 40 pulse we should get certainly TID less than 3%, which really qualify for typically Navy application even 2. So, coming for the design, considering that the input voltage of supply is Vs equal to VSC line voltage divided by root 3, and the 2 sets of 5 voltage sets each for each bridge, that is typically VA1, VB1, VC1 and VD1 and V1, that is for 5 lag bridge converter. Another set is for again VA2, B2, VC2, VD2 and V2 for converter 2. So, this is you can call it like a 5 phase rectifier, not in 3 phase rectifier, because we are converting 3 phase to 5 phase. So, finally, at the bridge we are having 5 phase like, and then you have a supply original supply of 3 phase here with the symmetrical supply of 3 phase, and from which we are deriving here 5 phase balance supply is one set 5 phase, and this is certainly the angle here is your 360 divided by 5, so that is a 72 degree. So, this is you can call it 360 divided by you can call it like a 5 phase. So, it will be like a 72 degree which you are having from one phase to another phase, and similarly for your second set of 5 phase you also have a typically another set of 5 phase supply. So, coming to the voltage for converter 1, I mean you have to get this voltage at typically 9 degree leading, and another voltage that is from B phase 90 degree leading, and then the C typically you can call it, this comes finally in that fashion. Similarly, for C phase 90 degree leading and for D phase for 90 degree leading, and then the E phase for 90 degree leading. I mean that what we have shown in the phasor, and of course, you have a input supply VA, you have a line voltage, this is the phase voltage, this is the line voltage. So, we derive in terms of line and phase voltage of the input, and of course, you can understand we are using here the 8 constant K12, typically even K12, K13 constant, total constant, and by geometric relation from inputs typically, I mean for second set of 5 phase, that is about all 5 phase second sets here. So, you all have another same set of the you can call it constant, because both sides of the voltage are symmetrical and identical, and then you have all these proper design geometric relation which is normally you could have studied in schooling. I mean from that you can get all these constants starting from K1 to K13 constant. So, these constants I mean is represented by you multiply the phase voltage, you will get the number of turns as much you are keeping for phase supply, or you have a you can multiply with the line voltage with these constant. So, you can get the number of turns or the voltage which are really required of each winding corresponding to these constant like So, that gives the design virtually for your transformer winding, and this is the input supply of you have a delta connector, and this is your what we discussed for the output for isolated. That was for non isolated, you have to use what we call it the you have to use typically the connection corresponding to auto connection, but here we have isolation transformer. So, primary is normal, and second is of course, we are using the kind of delta polygon connections for getting a proper phase shift. I mean from these 3. So, you can consider here you have again the set of all three single phase transformer you can have. This is you can call it horizontal. So, all the winding of horizontal you can see here which you are using typically several segment of horizontal. So, much segments of windings are there. I mean in once this first transformer secondary. So, you have 1, 2, 3 and typically 4 segment here in horizontal one. Similarly, you can have with the other 2 transformers. So, that give you the isolated connection for this typically 40 pulse converter, and this is the typically phasor diagram you can understand in that case. So, all voltage will be on the same circle, so that you have a phase voltage corresponding to all these 2 sets of 5 phase having a RMS voltage same. That is the reason this will be on the circle, and accordingly all these constants which we are showing as a turns K1 to K13, I mean we are able to get from this geometrical relation from different angle, as you can see here we can calculate, because that is coming in terms of the input voltage like. And now coming to this performance of this, typically I mean these transformer are typically designed and even developed in the laboratory also. I mean we develop it, and this is the typical case for when we are feeding induction motor drive. So, this supply voltage, this is current, and when during starting of course, it take more current from supply as well as the motor take, but once it comes to steady state almost at no load or little higher load, it draws more current, but you can see the supply current remain sinusoidal as well as balanced like I mean. And this is the TAD you are getting typically of 5.5% of the current at light load condition, and at full load condition you are getting the TAD of 2.23%. Of course, we are not considering the leakage reactance of the transformer substantial here, but you can adjust the leakage reactance and the TAD can be, this can be also reduced much lesser than even a 5%, and we are considering the typically a filter only the capacitive filter. You can consider LC filter, that also may reduce the typically you can get a typically the segment, and the you can call it the leakage reactance of the transformer you can adjust to further reduce the TAD of. And this is you can compare it because it start from 6 pulse. So, you can see the TAD at full load 6 pulse with capacitive filter, it gives not 32%, it gives 62%, and from 62 for 20 pulse you are able to reduce 5.5%, and for 40 pulse it is able to reduce 3.8% like. But if you could have a like a LC filter, then it could have been 31, it could be less than even a typically half of this around 2.7%, and this could be less than even 2% like. That is also practically possible by putting a small inductive filter at the output of this converter like on. So, that is about the performance you can call it typically of your 20 pulse and 40 pulse converter like. And this is the typically what it has been designed and developed in the laboratory environment, and these are typically the, you can call it the experimental results. I mean, you can clearly see that the TAD here varies like typically your 1.8% to typically 1.5% to 4.6% in 20 pulse, and it goes like a 2.2%, 2.7% in case of 40 pulse converter, like I mean also. So, it is always less than 5%, because in practical implementation you do not know how much is the leakage reactance, like I mean, and that really work out. Also, even if you do not use any even a capacitive filter at the output, you will get a good quality of the DC voltage, or you put a small capacitor, it also work very well, like. And the rating, of course, I mean it goes, this is the main transformer rating, this is the interface transformer rating, and this is the here of course for 40 pulse. 20 pulse you do not need the zero sequence blocking transformer, but you need for 40 pulse zero blocking, because you are connecting to 20 pulse converter in parallel. So, the rating of course here you can call it like it comes 56%, and here its rating comes 57.26%, like. So, still in auto connected is not going to be more than like 60% rating of the this auto connected transformer, like. And this is what the experimental results of 20% and 100% load, and you are getting 2% TAD, typically 2.7%, and here you are getting the TAD typically of again not much varying with the, and why it is not much varying, that depends on typically the voltage TAD also. Here voltage TAD is little higher, I mean of the supply, so that also reflected, and here TAD of the voltage is low, that is the reason both comes almost the same, like. And this is the 3-phase supply current along with the voltage, how it looks like almost like a sinusoidal current, and this is the of course the supply voltage supply current and load voltage load current. And these are the experimental, typically you can compare with this 40 pulse. I mean if you talk about the TAD of the current, like it start from 27 point and 12 pulse is 12.19, here 18 pulse 5.36, but 20 pulse is 6.9 and 40 pulse is only 2.5%, like. So, it reduces drastically down comparative results of this 40 pulse isolated converter, and this is the typical value you can see of the TAD, I mean in 20 pulse and 40 pulse, like I mean. So, it substantially reduces half, but already in 20 pulse also it is not going to be more than kind of 7% to typically coming around 5% also, but here it remains even order of like a less than 3%, I mean for the case of the 40 pulse converter with varying load from 20% to 100%, like. So, now coming to the another set of converter, non-conventional or unconventional converter of 28 pulse and 56 pulse converter. Here the only concept came that we are converting virtually the 3-phase supply with the help of this delta polygon transformer. We are converting 2 sets of 7 phases. I mean like this is one 7-phase set and this is another set of 7 phases, and that we are rectifying. This is giving 14 pulse here, this is also giving 14 pulse here. Using the auto connected, sorry, this interface transformer, we are able to convert into typically I mean 28 pulse converter. So, this here you will get a 28 pulse, and supply current also will get correspond to 28 pulse stepped waveform. So, it is able to reduce the total. So, you can even realize with the help of this like a 14 pulse or like a combining both you will get. So, you have a phase staggering, you are converting 3 phase into 2 sets of the 7 phase, and then we have a phase staggering, that is the reason we are getting 28 pulse. So, an angle for the each pulse will be 360 by 28, that will be the 1 pulse duration, and for 7 phase 360 by 7, that will the angle be from 1 phase to another consecutive phase, like. And this typically like if you want to go to 56 pulse doubling or by ripple injection, I mean you have to use ZSBT here to increase the from 28 to this is now you can call it like a 14 pulse, another 14 pulse. So, you are getting 28 pulse, but with the help of ripple injection circuit by this interface transformer and 2 diode, I mean like you can call it pulse doubling, we are able to get like a 56 pulse converter, like I mean or say here. And these are typically again that are auto connected transformer connections. I mean you have input supply, but all the output like which require 2 sets of the 3 phase here, 1 set of 7 phase, another set of 7 phase which are converting from 3 phase input supply from this 3 phase input supply. I mean they have symmetric 7 phase, this is another symmetric, but between the two you have interface. So, all this voltage should lie on a circle, so that you have a all equal phase voltage as well as I mean all equal phase voltage with respect to the transformer. Even the input voltage may be more or less, that accordingly you can design for. Now, with the this all constant, again here comes like a typical 16 constant. In case of previous case of your typically 40 pulse, you are getting 13, here you are getting 16 constant, because you have a several segment of a winding connection as you can see here. Why you are getting a 16 segment here, as you can see, even the input may be like a typically 3 phase supply, but the output segment are only of segment of these 3. So, you are using virtually 3 single phase transformer to realize this, like. and these are the 16 segment from geometrical relation, similar to like what you might have done geometry in the school level to find out from different angles or different angle relations like also. And this is the typical phasor diagrams, you can call it like for these all typically getting a 2 sets of the 7 phase with these different angles like, and this is the interphase transformer, like with the pulse doubling or ripple injection you can call it, and these are the typical relation which makes the pulse double in the connections like, and these are the different angles which we are typically finding for the design of this 28 pulse converter and 48 pulse converter. Virtually you are converting 3 phase to 7 phase and which giving 14 pulse and another typically kind of 14 pulse, and you are combining that getting 28 pulse and pulse ripple injection you are able to get like a 56 pulse from that. So, these are the typical angle for required for design, and you are getting 2 sets of the, consider that the input voltage of phase voltage of line voltage by root 3 and the 2 sets of 7 secondary phase voltage fed to each bridge, and these are the 7 phases virtually 1 to 7, 1 1 and 1 2, typically 1 1 2 1 1 7, and second set 2 1 2 2 7 for the second converter. And typically you can have it typically even for isolated case you might have a transformer turns ratio, these are the input supply, and these are the virtually 2 sets of 3 phase like 2 sets of 7 phase supply like you can say starting of VSA 1 2 typically your VSA 2 VSA 3 and VSB 1 VSB 2 and VSC 7 like and then the voltage you can find out typically from here how you will calculate typically from this VSA or VSA 2, VSA 3, all the segment in terms of these constant which we already talked about the constant there. So these are the phase your voltage you are getting here like typically, and realizing for B phase also similarly you will have a typically in terms of line voltage for C phase also, and these are the all 16 constant you are getting for this transformer to get made for the purpose of this converting 3 phase into 7 phase supply like. And now coming to the performance, so this transformer is also design and models, and these are the performance of the converter with the typically from 56 pulse. You can see current very close to sinusoidal, and the TAD here is only typically 2.4% with the supply current almost like a close to sinusoidal. Of course, it is tested with the variable frequency vector control induction motor type. You can see the 3 phase current of motor and typically speed, torque, and the DC link voltage also, and with the supply current this at one particular operating condition light load condition this comes 2.44, and this is the performance comparatively performance. If you talk about like a 6 pulse you are getting TAD 31%, but you get 28 pulse you are getting 3.6 and 56 you are getting 1.6% TAD like So, you are able to reduce the total harmonic distortion of supply current to order of like a 1.6% with this simple 56 diode based rectifier, and here you can see typically for the TAD typically order of 2.6% and light load condition, and you are getting typically 2.6% which is experimentally we have seen, and how it is with the 28 pulse and 56 pulse how it is varies with the load variation like. So, it comes you can call it the order of like a 1.6% here as we have already talked about, and this of course in case of 28 pulse is almost like a double per hour typically around 3.5% order of that, and how it is changes with the load like. And these are typically the 456 pulse 2 sets of we are getting a 7 phase from 3 phase input supply. Even for case of isolated topology, like you have a 3 phase input delta connected primary, and secondary you have a delta polygon. You are getting a segment of all these windings as a this. So, you are using only 3 single phase transformer, and we remember that you have a large number of the segments of the winding. Even if you see the horizontal one set of winding you have a 1 segment, second segment, third segment, you have a lot of like a 4th segment, 5th segment, 6th segment, 7th segment, 8th segment. So, you have almost like a 8 winding on the secondary and 1 primary. You have a 9 winding for virtually for 1 transformer. Similarly, you have a several windings on the typically, but it is a geometrical relation which you could have learned in the schooling, and you can do very well without much problem like. And these are typically the kind of the your polygon for 28 polygon. So, these are the different angles, and these are the typical kind of waveform for 3 phase supply. With the supply voltage 3 phase supply current, and these are the typically 6 pulse, that is a individual converter which you are having here, and then the interface zero crossing blocking transformer and the different winding segment, and the like a typically the you can call it like a typically the current of your typically coming from one bridge, and this is the total current like here. And this is the performance with the varying load. You can see the total harmonic distortion of virtually varying from 5.1 to 3.78 for 28 pulse, and for 56 pulse it is varying from 2.2 to 1.2% when you vary the load. So, that certainly give the you can call it the power factor close to almost unity. You can see in all cases, I mean third place up to 9, and then you have even a ripple filter ripple factor also goes less than 0.2 here in all cases like also. So, you are getting good quality input current, supply current with very low TAD, as well as the output voltage also with very less ripple in the output or ripple factor in the output like and this is the case of like a 28 pulse, and this is typically with the your 56 pulse converter. Now, coming to another set of this your non-conventional multipulse converter, 44 and 88 pulse converter, and this is what we do here. We convert virtually here 3 phase input supply with the help of this auto connected, I mean Polygon auto connected transformer. We convert 3 phase supply into 11 phase supply. I mean we convert initially for getting a typically 40 pulse, we converted 3 phase to 5 phase. For typically 56 pulse, we converted 3 phase to you can call it a 7 phase, and here we are converting 3 phase to 2 sets of 11 phase. So, this is 11 phase, this is also 11 phase, and that is the reason you are getting from bridge the double number of pulses. 11 phase gives the 22 pulse. Here also another set of 11 pulse, 11 phase gives you 22 pulse, and when you combine together it gives you 44 pulse here like also. And of course, this is the typically the magnetic rating. I mean it is a 56%, that is also the same rating as we are getting typically in case of 40 pulse converter also. And this is the how the auto connection transformer, this is the 3 phase input supply, but here also again you are using 3 single phase transformer. You can find out the one is typically one sets of vertical, I mean you can find horizontal segment, all depends on one transformer, separate windings you are connecting them, and you are connecting in this manner, and you can understand here you are getting virtually the 23 constant for designing of this transformer, and these are the phasor diagrams of all these. You can call it like a typically the 11 phase, 2 sets of 11 phase supply, and you are getting the, I mean you can call it like V11 and VB11. So, A sets of the 11 phase and B sets of 11 phase you are getting, and the angle which you are requiring here typically is given theta 1. I mean like typically between the phase is staggering, you are getting theta 1, here you can see edge here, and theta 2 is the angle between you are getting virtually typically between the 2 sets of the 3 phases. So, that is the angle corresponding you are getting from calculation, and the TAD corresponding to at 44 pulse you are getting order of 3.851%, and typically for your load full load conditions you are getting typically of 2.26% or so, and that is the performance you are getting typically here. The TAD total harmonic distortion you are getting 44 pulse from 2.646% to you are coming out of 100% at 1.34%, and in case of your 88 pulse you are getting from typically 1.39% to you are getting 1.2%. 1.27%. So, this is virtually what we are converting 3 phase to 7 phase also in this 88, and then you can compare of course from 6 pulse or typically from this here 420. We have already discussed like a 6 pulse where you have a TAD 27.97 and 12 pulse 12.19 and 18 pulse 5.36, and you are getting 20 pulse typically order of this depends on, and then 28 pulse you are getting at full load typically at full load TAD, and then on 40 pulse then you are getting 44 pulse, 56 pulse and then 88 pulse. So, you are getting TAD reduction for by increasing number of pulses, but of course, it also depends on your leakage reactance of the transformer as well as depends on the there is no unbalance in the voltage also like. So, coming to the conclusion of this non-conventional multipulse converter. So, design expression and performance evaluation of 20 and 40 pulse unconventional multipulse AC/DC converters are discussed, and the number of diodes used in 40 pulse converters is 22 only, which is less than even 24 or 30 or 36 pulse converter, and design expressions and performance evaluation of 28 and 56 pulse unconventional multipulse converter are discussed, and the 56 pulse converter employs only 30 diodes, 28 plus 2 means 30 diode, and you can call it TAD of this you can call it means less than 5% at varying load in 28 pulse converter, and the rating of the 28, 40 and 56 pulse converter is less than the 18 pulse converter, and the rating of the non isolated I mean 28, 40, 56 is only typically you can call it 50 to 60% of load rating in auto connection, and design expression of and performance analysis of 44 and 88 pulse converter and unconventional converter also discussed. And these are the typical references, I mean like which we have referred for this work, and thank you.